So, hello everyone, I'm Vasco. We're getting closer to the end of this workshop. I will be telling you something about hierarchical inference. At the end of the talk, you will be able to play with this very funny game I put you here. Right, so just for a quick recap, you heard about all of these things before. So you heard about how to build an interferometer, how to use it, how to get the data, then how to process the data, how to detect events and how to quantify that, and lastly, about how to measure parameters and get estimates for the binary. Is there anything else we can do? Well, if you're here, I guess the answer is yes, and this is what I'm going to talk about. So I will be talking to you about how to combine events in general. Then I will be moving to the applications, what are the most important science cases, and then I will conclude with some methods and some more technical notes. Sorry, there is some delay. All right, so let's get started. The problem is the one in which we have a collection of observations. We have a collection of observations that you can see here, for example, in this drawing. These are our observation with their measurement uncertainties for these different colored Gaussians here. And we want to take that and combine them in such a way that we're able to infer the properties of the distribution from which these observations have been drawn. So their population. The way in which we do it is again through Bayesian analysis. This is our statistical framework. It's gonna take some time. Right. So it's the same thing as Charlie just described. So we want to get the probability distribution of a model given the data. You can see here in the equation on the left, if we're able to model the probability of the data given some model. In this case, differently than what we just saw for a single event parameter estimation, the ingredients are different here because the likelihood is now a hierarchical likelihood, is the one in which we take the single events as input and we combine them to get hierarchical second layer of analysis. And the model is that of the population, is not that of the waveform. And the parameters that we will infer here, which are called big lambda, are not the ones for the single events again, but are the parameters that we use to parameterize the full population. So as you learned before, the most important things in all of this the scheme is how to get a proper model of the likelihood, which is what we're going to do now. So I will talk to you how to derive a very general formulation of the likelihood, starting from a simple case. So let's consider a simple case in which you can see here in the top right, we have a population. This is just an example of two Gaussian distributions. So first of all, what are called the population parameters, this big lambda here? These are the parameters. For example, for these two Gaussians, we have the mean of the Gaussian and we have the standard deviation of the Gaussians. We also have a relative weight, since the full distribution needs to be normalized. And in this framework here, let's assume for the moment that we have a perfect measurement. So we have a collection for which we have direct access to the true parameters. In this case, the likelihood, given that the observations are independent, just reduces to the product of the population distribution evaluated on our observations. And if for example, I generate a population drawing 100 events from this distribution here, then I use this likelihood and I get on the bottom right, you can see the corner plot corresponding to the samples for the posterior distribution of these parameters. These are exactly the parameters I described before. These are the mean of the two Gaussians, the standard deviation, and the relative weight here. So what you can do is you take one of these, each of these samples, as I said, correspond to one population. So you're able to take one and plot a curve corresponding to the distribution that you sampled. You take a second one, you keep going on, and you end up with this bundle of curves corresponding to the samples on the population parameters projected as a population. And here in dashed, you see the true distribution. So you see that overall, we were able to recover pretty much the underlying shape from which the events have been drawn. And this is a very interesting tool because you can define some statistics over this bundle of curves and, for example, represent the median of your reconstruction and the 90% credible interval of your reconstruction, which gives you the uncertainty for which you were able to constrain the underlying population. Now, just to show you, if I repeat this exercise, changing the number of events in the catalog with 25 events, I get this green curve. You see that the uncertainty is very wide because we have few events. So the constraints, the posteriors on the population parameters were weaker. And is reflected in the reconstruction distribution with 100 events. This is what you saw before. And if you keep increasing the number, the 1,000 events, then you get pretty much get a very accurate reconstruction of the distribution. Good. So we know how to deal with this very simple case, but unfortunately, our measurements are not perfect, and we don't have access to the true population parameters. We get the data. So we need to find a way of moving from the data to the actual parameters of the single events. This, as Charlie just explained, is done through the likelihood of the single events. So the way in which the likelihood, the hierarchical likelihood modifies is that now instead of having the direct product of the population distribution evaluated on the single events, you have to marginalize over the unknown true parameters of the events. And this is done by convolving with the likelihood of the single events, which by definition gives you the probability of the data given the parameters. So you have to go through this integral here for all the events that you have in the catalog. Now, if you do this, I'm comparing here in blue is the analysis with the true parameters only, the example we saw before, and in red is the one in which you have also some Gaussian uncertainties on these measurements. And you can see that the reconstructed distribution is wider, like the uncertainties are much higher because of this, because you're introducing an additional element of uncertainty in the analysis. Good, there is a third ingredient which is very important, is the fact that our detector is not perfect. Therefore, we cannot measure all the events with the same sensitivity as we pretended up to now. And in other words, we need to account for selection effects. Let me show you how this works in practice. So, for example, you can see here on the bottom left, this green curve corresponds to the selection function, so the probability distribution for detecting some events that I'm inputting into the analysis. I'm pretending here that events with positive X have a detection probability of 1, so they always be detected without no problems. But the events with negative X have only 20% of being detected, right? So what I'm doing here, I'm generating the same population as before, 100 events. I take the events with that came out with a negative value, and I only consider as detected that make up my actual catalog of observations, those 20% of them. If I pretend that my detector is perfect, so I don't have any selection effect, and I just run the analysis with the likelihood of before, I get this red curve here. So as you see, since I observed less events for negative values, now I recover a distribution that is much lower. And since the distribution is normalized, now the positive values have a larger peak. If I properly account for selection effects, then I'm able to recover the correct true distribution. And this is done because for positive values, we said that p-det is equal to 1. Therefore, this terms is 1. The population distribution is normalized, so the whole integral is basically doesn't contribute to the likelihood, and you end up with the same likelihood as before. For the negative values, instead, you have smaller values, which makes the denominator smaller, and therefore you're compensating with a higher value of the likelihood by manually introducing the detection probability. And if you look at the relative weights that you have inferred, without this correction, you get a biased value, and with the correction, you get a proper one. Okay, so this is important. Just a quick summary. This is what I just discussed, these three cases, and this is the pretty general formulation of the hierarchical likelihood that we will see applied on real data in a moment. So before moving to the results, I just want to highlight a couple of properties which are important. So the first one regards selection effects. So we know that for gravitational waves, for compact binary mergers, the probability of detecting them really depends on the mass of the system and the distance of the system, for example. This is represented here in this plot, in which I just took generated events from a flat distribution in the primary mass and in redshift, is the blue curve that you see here. And the red ones correspond to the ones that have been detected with that passes some SNR threshold at a 4 sensitivities. This is just an example, but it's to show you that the distribution of the observed events, the red one, really differ from the intrinsic one. So for example, events very close in redshift have a higher probability of being detected, but if you go farther, then the probability drops down as expected. If you go farther enough, then probability p det is basically 0. There is no chance you're gonna observe an event. But something similar happens with the mass, because the mass of the system determines the frequency, and the frequency, of course, based on where it is placed in the sensitivity curve of the detector, implies that high mass events, for example, are more likely to be observed, and low mass events is the opposite. So you can think of this like a filter. The detector filters the intrinsic astrophysical distribution based on the property of the events. But it also means that all the observations that you're trying to reconstruct with your population analysis that correspond to regions where you are less sensitive, you will have a lot of information that is extrapolated. There is nothing we can do about that. It's just the fact that if we don't observe anything somewhere, there is no information coming from there, and we need to account for that into analysis, but there is something that you're assuming. Last thing is that we have a finite number of observations. So an actual distribution is defined by an infinite number of events, of droves. Here we only have a finite number. That means we are subject to Poisson noise, like specific realization of the population. This is something that is taken into account the likelihood I showed you before. But this is also a property that can make a difference for small catalogs. Right, so the last thing, this is the last technical slide, let's say, is just wanted to show you how these integrals are done in practice. Because we're talking about very integrals in large dimensions. So there is no hope you're gonna do that analytically. What we do is that we compute them with numerical integration by random sampling. This is Monte Carlo. For those that don't know, I am just showing here briefly what's the idea behind. The idea is that you can compute an integral, you see in the first equation, as the sample mean of the function evaluated on a collection of samples drawn from a uniform distribution. And this idea can be generalized with arbitrary distributions and in arbitrary dimensions in such a way that the integral of a probability distribution that multiplies a function can always be expressed with sufficient number of samples through this sum here, given that the samples follow the probability distribution P of theta. And the larger the number of samples you have, the better your estimate will be. So a applied to our specific case, this is, for example, the numerator of our hierarchical likelihood. Remember, we have the likelihood of the single events multiplying the population. Then it means that we will be able to compute this integral by evaluating the population on the samples of the, not the likelihood, because we don't have access to that. We do have access, however, to the samples of the posterior distribution of the single events, which is is proportional to the likelihood multiplied by the prior. And therefore, if you divide by the prior, you can compute Monte Carlo this integral. And you get something similar for the numerator, so the selection effects integral, if you have samples distributed as the detection probability distribution. Right. So moving to the applications, I will start with talking about the population, the distribution of the black hole mergers we have observed, because what do we do with all of this machinery that we have talked about up to now? So in this case here, our population distribution is given by, you should have understood by now that the single event parameters are the masses, the spins, the distance of the binary black holes. And therefore, we can express the population as something like that. This is a multidimensional probability distribution. And if we run the analysis using our parameter estimation of the single events, given our catalog, then we can reconstruct the population of these parameters. We can also use a combination of different parameters. For example, instead of the masses, we can use the mass ratio or the chirp mass. Instead of component spins, we can use the effective spins or processing spin. But the idea is the same. And you get distributions like these ones, which are taken from the LVK population paper. You see here, for example, in top right, the distribution for the mass ratio, then distribution of the redshift, distribution of the spin. And here, the big one is the distribution of the primary mass. How to read that? Well, if you take the primary mass, these are is the value of the primary black hole expressed in solar masses. And you can see that the distribution, for example, has a global maximum about 10 solar masses. Then it goes down in probability. There is another overdensity about 30 solar masses. And again, here, the width of these curves represents the uncertainty that you got from the estimation of the population parameters. And the different colors are different methods, different ways of modeling the population. But I will be talking more about this later. So I also put here reference for some introductory reference on this topic. What do we do with all of that? Well, we can learn some astrophysics, because now think that this catalog of events come from some physical merging of black holes that are scattered around the universe. But for that, you need to first create black holes from stars. Then you have to bring black holes together. And you can think of infinite ways of doing this, but the actual universe is only one, which means that there will be a collection of astrophysical processes that contributed to the actual catalog that we have observed. Which means that if you can ask some astrophysical, you can ask astrophysics, and they will tell you what are the most likely channels for the formation of these mergers. And you will try to see in the data whether you're able to understand or to find any specific signatures for these channels. Now, without going too much into the details, I put here what are the most representative channels. For example, you can form these black hole mergers through an isolated evolution. So these are isolated binaries in which you have to start with two stars, then you form black holes from there. They get closer through several processes, then through gravitational wave emission, and then you have the merger. But they mostly spend their life together. For example, following this idea, you would expect the spins of the binary to be mostly aligned with the orbital angular momentum. Instead, if the binaries have formed in a dynamical environment, then you have like think of a center of globular cluster or a stellar cluster. You have a lot of body or compact body interacting. Therefore, when you actually get a couple of pair of black holes merging together, you would expect the spins to be randomized. This is something that may not be trivial to observe from a single binary, but if that is true, then you would see this behavior at the population level. And this will be a clear signature of distinguishing one of the two channels. Another one, for example, is the idea of repeated mergers. So you can first form a black hole, then a binary black hole merger. So they merge, they form a new black hole, then somehow you get closer to another black hole and you form another merger. And this is a second generation merger, which is partially related to the dynamical formation channel, but in principle, you can have as many generations of mergers you want. And the idea is, again, to look at the data and try to distinguish between these. Most likely, the actual population is given by a combination of these. And one thing that you can try to infer, for example, is the ratio between them by estimating this parameter relative weight, as in the first example of the two Gaussian I showed you before. So another class of application for this population analysis is cosmology. So I talked to you about masses, distance, but you may know that there are some complications in that, because the actual mass and distance that we observe when the signal arrives to the detector is not the true one, but is the one affected by the large-scale dynamics of the universe. As I quickly show here in the top right, you see that once the gravitational wave signal is created and it propagates up to us, it is affected by the underlying dynamics of the universe, and it gets stretched. It gets stretched if the universe expands, for example, in such a way that the mass that we observe in the detector is multiplied by this 1 plus z, where z is the redshift, and it contains information on cosmology. And the distance is the actual luminosity distance. It means that if you take one event, this redshift, unfortunately, is completely degenerate with the other parameters in the waveform, so you cannot measure cosmological parameters by itself. But if you combine on a population level, you would see that, given that all events are redshifted this way, features in the population distribution will be tilted, and the tilt depends on the cosmology. Therefore, the population has some information on the cosmology, and we can exploit that to learn about that and to constrain cosmological parameters. So this is what is normally done now. So for that, you just need to take the inference we described before with all these hyperparameters that model the population, and you just add the cosmological parameters as additional population parameters. And here, for example, are the posterior distribution that you get for the Hubble constant, which is the local expansion rate of the universe. Specifically, this orange line, which is called spectral siren. This is just jargon for population-based cosmology without any additional information. What you can do, though, in the case of cosmology, is to combine this approach with additional information from galaxy catalogs, for example. And the key point, the underlying message, is that today gravitational wave cosmology is mostly based on population analysis and a joint combination of the population of binary black holes together with possibly additional electromagnetic information. So a third example is fundamental physics. And regards test of general relativity. So you already heard that we can test fundamental physics with gravitational waves. This is there are several frameworks for doing that, but the main idea is that you can add some parameter that describes deviations from GR and constrain those parameters so that if they're centered at 0, then they're consistent with GR. Otherwise, you're measuring some deviation, given a lot of caveats. But so here I'm reporting 2 plots for 2 different analyses from the LVK paper again. One is including deviations in spiral, and the other one is including deviation in the post-merger. If, suppose you analyze one event and you get one deviation, are you going to claim that you have observed a GR deviation, especially given everything you heard about the properties of the noise, the detector characterization? That's going to be very hard to believe. Therefore, like a proper GR deviation should emerge coherently from the population. So it should be something to be measured at the population level. And this is why the collaboration does test of GR by combining events. Right, so moving towards the conclusions, I'm gonna talk to you about what are the ways in which we actually parameterize these populations. So what are the methods that we use? I'm gonna divide this into 2 main classes of approaches. So we have like strongly modeled approaches, which are often called parametric. And this means to specify like a phenomenological function for the distribution. This is easy to do, easy to implement, and possibly easy to interpret. On the other hand, since again, we don't know, we don't have access to the true underlying distribution, it also means that we are more prone to systematics if you choose the function that is not properly representative of the distribution. The other class is weakly modeled approaches, in which you have a more agnostic reconstruction of the distribution from the data. These approaches are more flexible and less dependent on prior assumptions. On the other hand, they may be more difficult to interpret in some cases and may be more prone to overfitting. So just to show you how this looks like, if we take again the distribution of the primary mass, we can see that for strongly modeled approaches, you have this mostly means taking combinations of Gaussians and power laws. And you can see here in orange how the same distribution that I showed you before looks like if you assume a model that is just made by a power law plus a Gaussian peak. And before and below in pink, this is a model in which you have like a broken power law, so 2 power laws plus 3 Gaussian peaks. And you see how the distribution changes to the point that in some places it can also be statistically inconsistent, the reconstruction. And this is just because you made different assumptions. On the other hand, here on the right, you see a collection for different weakly modeled approaches, being Gaussian processes, B-splines, mixtures of Gaussians, autoregressive methods. And I tried to put here a collection of papers that describe all these methods here, if you want to take a look. The key point is that the reconstruction really depends on the methods and the way you parameterize and the assumptions that you make in your analysis, even though they agree overall. Finally, I will conclude with a quick snapshot of some of the results that we have today. This is just to show you that this is a very active field of research. And I wanted to get to know what people are more or less working on in these different areas. So for astrophysics, for example, people are looking for correlations on a population level, for example, like dependencies of the mass of the systems with the spins or the redshifts. And this is closely related to the identification of potential subpopulations in our data sets. Another thing that people are working on is to bridge this population analysis with astrophysical population synthesis codes, so like equivalent of the theory for the underlying astrophysical processes. For cosmology, it's systematics, how population biases affect the measurements, machine learning-based inference, the inclusion of backgrounds, for example. And for test of GR, it's mostly the development of a full analysis, including the population parameter, the astrophysical parameters within the population. And I have like a quick slide on some of, I think, are the most recent developments in this field. This is implies, for example, to direct sample the full hierarchical likelihood, including the event parameters, some non-parametric to parametric mapping, some sampling directly the observed distribution instead of the astrophysical ones. Again, I put references here for people that may be more advanced and more interested. And I will conclude just mentioning what I believe could be considered open problems in this field. Just to convince you again that this is something that is pretty recent and there is still a lot of work to done. This is numerical stability, for example. What is the best strategy to control numerical instability in these Monte Carlo integrals? Figure of merit, how to distinguish between which analysis is better than others. How to control the prior assumptions and how to distinguish, how to rank different reconstructions which use different assumptions and methods. And also scalability, like we would like to have like a full multidimensional analysis with correlations, which comes with a high computational cost, especially for larger catalogs. So a lot of work to be done. I will leave you with my conclusions. The last thing, if you want to play with that and get your hands on, you can find the Open Data workshop tutorial on hierarchical inference in the additional material, and you're happy to take a look, and you will be welcome to take a look. Thank you very much.
Thank you, Vasco. So as Vasco just mentioned, this topic is slightly outside of the core of the workshop. Don't spend too much time on it for now, but we think it's very interesting for you to go a little bit further. Okay. I think there's no question online. Let me check again. No. Up. No need for questions, right? Any question in the room? We have one.
So thank you for the interesting talk. My question regards cosmology through gravitational waves and the spectral stereo method. As you mentioned, the main results we have are throughout the analysis of spectral sirens because we have more binary black hole events than binary neutron star events. However, how many more observations would we need of binary black holes to have a measurement of H0, which is, let's say, competitive with the one through bright sirens when observing instead spectral sirens? Thank you.
Yes, well, first of all, let me say that I haven't talked much about neutron stars, but this is, of course, another population that people are very much interested into. So regarding your question, it really depends on the actual underlying population, because the way in which you gain information for cosmology is by having sharper features in the population. And if your population was flat, then you can have how many events you want, and you will never get like a highly constrained measure on the Hubble constant. So based on what we have now, we are getting pretty close, or probably we are already there, to the amount of uncertainty of the only bright siren event that we got so far, 170817, with catalogs of 150 and possibly more with GW2026. Even though, again, it really depends on the population model. It depends on the parameterization that you use. If you enhance somehow, or if you recover sharper features, then your measurement gets better and you can increase the measure deconstraining power on H naught.
Thank you. Any other question? Yes.
Thank you very much. Maybe you mentioned this, but if we are looking at hierarchical processes, then probably the population we're talking about is evolving with time and redshift. So there is not one underlying population, but a population as a function of time. What do you think about that? If there are hierarchical processes and so black holes grow through, okay, you got it, then there is not really one underlying population, but an evolving population through time.
Yes, absolutely. Well, this is something people have been looking into for a few years now. And with increasing catalogs, we're hoping to get some more, let's say, robust answer in the next few years. So for now, I wouldn't say there is like a general consensus on having hierarchical mergers underline the distribution, even though one very common argument is that astrophysically you expect to have like a drop in the rate at some mass scale of about 50 solar masses. And all the events that have larger mass would be made by hierarchical mergers, even though it's difficult to disentangle these subpopulations if they're there. And I would also say that, so as you probably got, like, to separate these astrophysical processes, you need to get information from the spins, which is something that we are kind of lacking now. And this is something that is not only coming from the number of events in the catalog, but also from the accuracy in the single event parameters. So I also have the impression that we would need higher sensitivity in the detectors to be able to have better constrained spins, and therefore being able to separate between different channels at the population level.
Thank you. It seems we really need future detectors, right? Hey, what's coming now? Okay. Any other question? I don't see any question in line. No? Well, so we would reconvene at 4 for the talk on future detectors. Isn't that wonderful? Thank you again, Vasco. And thank you for the great discussion. We'll meet at 4.